try to plot the graph. Okay, so let's use the same function. Okay, so right now we're just going to do, we're not doing some computations here first. Okay, so let's say your time will be from 0 to 12 with increments of 2. And then these are the values of velocity numerical. So 0, 19.62. We're going to do this in a more formal way. This is just for illustration. So 36.41, 37. 5123, 51.6008, and 51.6938. These are your values. Okay. Okay, so let's try to run this first, just to verify the values. Okay. So now let's plot. Of course, we have to turn on the hold on, and then let's plot. And your velocity numerical. And let's say this is in solid lines with circular markers that are red in color. And then here. And let's run. Okay, so as you will notice that this is your numerical solution and this is your analytical solution. Okay, of course, let's complete this by making a legend. The first part would be analytical. What would be numerical?
Sir, yung G po nung nauna, 8.91.
This one? Ito ka?
Di ba? Dun po sa code. Nagkapalit po ata yung 9 tsaka 8.
Okay. 8 point. Okay, sure. Okay. Then, okay, thank you for pointing it out. So location should be, yeah, let's do bests. Okay, so let's copy the output and let's paste it here. Okay, we're going to delete this and paste it here. And then, okay. Okay, so as you notice that the numerical solution captures basically the essential features of your exact solution. Okay, that it is increasing at start rapidly, and then at a certain point in time that increasing speed suddenly decreasing. Okay, so the large acceleration at the start, and because of the drag force that opposes that downward gravitational force, the bungee jumper slows down as time progresses. So basically, the analytical solution and the numerical solution provides you essentially the same features. Okay, but as you will notice that if you are going to if you're going to see there are differences between the values, if we're more concerned with the exact or the more exact value of the velocity of you when you fall down, you will notice that somewhere as time progresses, the difference between the numerical and the analytical solution increases. But at a later time, that difference will be closer to each other. Okay? And that is because of the fact that what we did is only an approximate. And from this definition of derivative, the exact derivative of this function, the exact derivative of this function would be approached by our numerical solution if we make this delta t, or the interval between delta t and the interval between two time intervals, to be as small as possible. Of course, it can never be 0 because when this step size is 0, therefore, there is no progress in the solution. Okay? So if we're going to do this in a code, you can see that when you change the time interval to be smaller than this, to be smaller than 2 seconds, your numerical solution will approach your analytical solution. Of course, this is already solving differential equations, and that will be a topic of another day. So this is just to illustrate to you how we do numerical methods. And therefore, this makes this numerical method always entails some kind of error because this is an approximation method. Okay, so that's why it is important to analyze these errors in order to see whether the numerical method that you're going to employ somewhat approximates properly your analytical solution. Okay, so in the next part, we're going to go to some basic error analysis for numerical methods.